We finished thermodynamics last week, and so now not last week, the week before last week. So now let's jump into electrochemistry. We're only going to do 2 days of electrochemistry, right? So it's pretty short. Um, but it's basically a good little extension from delta G and stuff when we're talking about electrochemistry. Okay. So what is electrochemistry? Electrochemistry is the study of the relationships between electricity and chemical reactions. This includes the study of both spontaneous and non-spontaneous processes. So you see how that goes back to us talking about thermodynamics 2 weeks ago, right? It connects back to that. And when we're talking about electricity, what we're really talking about is the flow of electrons, right, in reactions. Okay, the flow of electrons in reactions. So if we take a look at give subtitles. Why do I need subtitles? I don't need subtitles. That's weird. Okay, so if we take a look at what the gist of electrochemistry is, which what we're talking about here is basically oxidations and reductions, right? Because that's the loss and the gain of electrons. Okay. So first thing we got to figure out is how do we do like oxidation numbers? And this is just it's not even a figure out. You've already done oxidation numbers back in Gen Chem 1. So it's not really a figure out, but it's just a little reminder, right? Remember that elements, like elements on the periodic table, they all have oxidation numbers of 0, right? Most of the time, though, they're not happy with that because they want to, pull electrons from somewhere else or lose electrons to get to the octet of 8, right? To get a full shell of 8, an octet, and then their oxidation number will change. But as is, though, on the periodic table, elements have an oxidation number 0, right? Monatomic ions have a charge. So, example here, remember that fluorine has a charge of -1, right? And then oxygen has a charge of -2, right? Unless it's two oxygens together, like peroxide, then it's got a charge of -1. And then hydrogen here, which is basically a proton, has a charge of +1, unless that hydrogen has an electron attached to it, and then it becomes a hydride, and then it's got a charge of -1. And we actually talked about hydrides a lot last couple weeks ago, because it's a hydride plus a proton that gets added to NADH or NAD to become NADH and FAD to become FADH2 in glycolysis and the TCA cycle, right? So we've heard of hydrides before. So the sum of the oxidation numbers overall in a compound will then equal 0 in a compound, right? So the charges will all equal out to 0. But when you have those ions separate, each one can have its own oxidation number. Okay. So let's just quickly look at this here, right? To keep track of what loses electrons and what gains them, we assign them oxidation numbers, like I said before. And if the oxidation number increases for an element, then it's oxidized, right? If the oxidation number decreases for an element, then it's reduced. So basically that means that if the oxidation number goes down, the element gained electrons. If the oxidation number goes up, it lost electrons. Okay? Does that make sense? It's a big thing right there. Okay, so we're going to use this example here. I think this is the example on the next slide. I hope it is anyway. But here we have zinc metal, right? And we'll add to it some hydrochloric acid, and then it becomes zinc chloride and hydrogen gas, right? Hydrogen gas. So this actually is a redox reaction, right? This is a redox reaction. And you can see here, for example, zinc here actually had 2 electrons, had a single electron, right? But then it lost that electron and it became zinc chloride, right? So this is definitely a redox reaction. So let's actually look at it very closely in the example ahead, except that we have our first question. So the vast majority of you got this correct. The answer is in fact D. I'm gonna have to figure out who that was. I got it wrong. It means they weren't paying attention. I'll look that up in a minute. Okay, so let's keep going. I don't want to waste time on this. I'm just playing with you guys. Anyway, so let's talk about this again. We've talked about this so many times, right? When a species is oxidized, it loses electrons. So as I was saying in that reaction we saw in that picture, zinc loses 2 electrons, becoming the zinc chloride, right? I'm sorry, becoming the zinc 2 ion, which becomes zinc chloride in the reaction, right? Which I'm sorry, I think I may have said zinc 1 previously. It's actually zinc 2. And then the species that was reduced, right, gains electrons, and the thing that got gains electrons is the protons. It got an extra electron, right, forming H2 gas, right? So the oxidizing agent here, right, an oxidizing agent here, which is proton, causes something else to be oxidized, whereas the reducing agent causes something else to be reduced, right? So we have the oxidized species, which is the thing that lost the electrons. We have the reduced species, which is the thing that gained the electrons. But then we have the oxidizing agent, which did the oxidizing, and then we have the reducing agent that did the reducing. Make sense? So basically, the agents are the opposite of what? The oxidized and reduced. Okay. So, like I was saying before, we're sticking with this as our example in our redox reaction, our oxidation reduction reaction, right? We begin here with zinc solid, right? And zinc solid here is introduced to protons from the hydrochloric acid, right? And so zinc here has an oxidation number of 0, right? Individually, each proton has an oxidation number of 1, okay? And then what happens is that the zinc loses 2 electrons and becomes 2, zinc 2 plus, right? And then the hydrogens gain the electrons and they become hydrogen gas. And so now the oxidation number of zinc is 2 plus or plus 2. And then the hydrogen gas has an oxidation number of 0, right? And you see it in the equation as zinc chloride, right? Uh, but here, we're just talking about the species that are losing electrons or getting electrons, right? The zinc lost electrons and became plus 2, right? And the hydrogen gained electrons and became hydrogen gas, okay? So back in Gen Chem 1, we did this thing called balancing chemical equations. If you recall that, you all recall balancing chemical equations, right? Well, now we're going to have to do what we call balancing redox equations, oxidation reduction equations, and they're a little bit more complicated, just a tiny bit, right? And so when we want to do balancing of an oxidation reduction reaction, we have to use what we call half reactions. Okay, what we have to use is what we call half reactions, right? So in an oxidation reduction, they're written balanced separately, right? We will use them to balance a redox reaction. So for example, when tin 2 and iron 3 react, right, we get here the 1/2 reaction is with tin here losing electrons, right? So tin 2 becomes tin 4 and then plus 2 electrons. And in the reduction part, iron 3, right, gains those 2 electrons and becomes iron 2, right? So in redox reactions, we have to split the reaction in half, right? The reduction side and the oxidation side, right? And we have to balance them separately. And you've seen here already, part of balancing it is balancing it by putting coefficients, right? Which you already know about, right? Which you've done before. But then you also have to balance out the charges by adding electrons, okay? So, let's see here, right? Okay, so this is just a synopsis of how we balance half equations, okay? How we balance half equations, or balance redox equations using the half reaction method. First thing you do is you take the reaction, the redox reaction, you make it 2 half reactions, an oxidation reaction and a reduction reaction, okay? And then you start out by balancing all the atoms with O's and H's, right? With O's and H's. Sorry, let me say that again. You balance out all the atoms other than the ones that are O's and H's, okay? So if you have anything else in there like zinc, chloride, anything that's not an O and not an H, you balance those first. And then when you get to the O's and H's, you got to balance those. You balance those out by balancing them using waters and protons. Okay? Waters and protons. After you do that, you add electrons to balance the charge. And then you multiply by the common factor of the electrons so that you have the same number of electrons on both sides of the equation, right? They end up canceling each other out. And then you add the half reactions to each other. And then you have the full reaction, okay? So then you simplify so this is if you have a base, right? If you have a base, you simplify the reaction by dividing by the common factor and canceling out any waters that came from adding protons to hydroxides. So the thing that's confusing about this is that when you do a redox reaction that is in acidic conditions, all you really have to use is waters and protons and electrons, okay? But then if you're doing it in a basic solution, you've got to use all those 3 things plus hydroxides, right? And those hydroxides turn the protons into waters, and those waters can get canceled out after you do the adding of the thing, right? And I know the steps are kind of difficult right now, but when you see it happening, it's actually really easy. So last thing you do is you check, and what happens is that when you're completely done, both sides should have the same number of atoms, like you should always do in a balanced chemical equation. But the more important thing is that the both sides will have the same number of charges, right? If one side has a +6 charge at the end of it, the other side will have a +6 charge at the end of it, right? If one side has all the same number of oxygens, the other side will have all the same number of oxygens. If one side has all the same number of protons, same thing on the other side, right? So our next question is this. Which of the following is not a step in balancing redox reactions? Make two half reactions, right? Balance atoms other than O and H, and then balance O and H using waters and protons, right? You subtract electrons to balance the charges, or you multiply the common factor to make all the electrons half reactions equal. All right, let's see how people are answering this question. I know it's a rough day. I know it's a rough day. It's rough for me too. All right, I've got 3 people in. Still waiting for 4 more people. 3 more people. Oh, dang, I forgot my drink. Dang it. Okay, everybody's in, and I am so very proud. It means everybody's paying attention because everybody got that one right. There is definitely no subtracting. Whoops. There is definitely no subtracting involved in the balancing of redox reactions, right? So good job. Everybody got that one correct. The answer is indeed C. Good job. Okay. Okay, so let's use this reaction now as our example reaction for doing redox balancing, right? So this is a reaction between permanganate, the ion, right? The MnO4 minus is permanganate, I'm pretty sure. And then the other ion here is oxalate. I'm pretty sure it's oxalate, right? So usually in this kind of reaction, remember when you did a acid-base titration, right? Well, this is what we call a redox titration. And the species or the chemicals we use in redox titration are generally potassium permanganate, which is the purple color, and the oxalic acid, which is the clear color, right? And you do a titration the same exact way as you would do an acid-base titration. But we still need to balance out these equations, okay? So that's why we know then that this is actually the permanganate ion and this is the oxalate ion, right? And so this is the redox reaction we have. Permanganate, which is MnO4 minus in aqueous solution, plus oxalate minus 2, right? 2 minus in aqueous solution, becomes manganese, right? 2, and then carbon dioxide in the solution, right? Carbon dioxide in the solution. Okay, so first thing to do, right? First thing to do is assign the oxidation numbers. Okay, we see that manganese here began with a +7, right? And then it became a +2, right? And then carbon, so that means that manganese got reduced, right? When you go from +7 and you go down, that means you got electrons. So that's a reduction. So manganese got reduced. And then carbon dioxide, right, got oxidized, right? It went from a +3 to a +4, which is interesting because you already know from previous lectures that when you add on oxygens, that's automatically an oxidation anyway, right? That's why we call it oxidation, right? And so in this reaction then, manganese is the one that's getting reduced, carbon is the one that's getting oxidized, right? And those are the oxidation numbers, okay? So let's go ahead and split them up into the half reactions, right? So here we have the oxidation half reaction. Oxalate becomes carbon dioxide. And so the first step was to do what? Balance everything but the what? oxygens, and hydrogens, right? So we have a single carbon on the right side. We have two carbons on the left side. How do we balance this? All we have to do here is to put a number 2 as a coefficient in front of carbon dioxide. And now we have two carbon dioxides on the right side, and we also have 4 oxygens on the right side, which is the same as it is on the left side, right? Good stuff, good stuff. See, this part's the easy part, right? So next, right, the problem now, though, is that once you've balanced it, right, once you've balanced it, you still have a -2 charge over here, but you have a 0 charge over here, right? So the way you balance this charge-wise, right, is by adding 2 extra electrons, right? So now these two right here, -2 right there, is balanced by these 2 electrons over here, okay? And you might have to add electrons on either side. It just depends. If you're doing an oxidation reaction or a reduction half reaction, right? But on this one here, carbon dioxide is definitely getting oxidized, right? And so since it's getting oxidized, you can see that it becomes 2 electrons separated from the carbon dioxide. And that's why you know this is an oxidation half. And so remember, -2 on this side gets balanced out by 2 electrons on that side, okay? So we're done balancing the oxidation side of the half reaction. So now let's do the reduction side of the half reaction. We have manganese here, right? Or permanganate rather. And permanganate became manganese 2, okay? And so how do we balance out oxygens? Well, we balance out oxygens by using water. So you need to have 4 oxygens here, right? You need to have 4 oxygens to balance out the number of oxygens that are on the left side. How do we do that? We add 4 waters because that gives us 4 oxygens. Does that make sense? Right? We have 4 waters because that gives us 4 oxygens. Okay? Then we've got to balance out all the hydrogens that we put out here on the left side, on the right side, right? All these hydrogens from the water here. So there's a total of 8 there. How do we do that? We balance that out by adding 8 protons to the left side, right? So now there's 8 protons or 8 hydrogens, and there's 8 hydrogens right there, right? And then there's also 4 oxygens, right? And then we still have 1 manganese. So all the atoms are now balanced, right? But what's still not balanced yet? Exactly, the charges are not balanced yet. Okay, so now we got to balance the charges. So to balance the excuse me, I'm gonna have to cut that out. It's gonna be very loud on the video. So to balance out the charges, right? To balance out the charges, we have 8 positive charges over here, right? Plus a minus charge here, so that actually gives us a total of -7. I mean, sorry, +7 on this side, and over here on this side we only have +2. So how do we get the +7 down to +2? We add what? 5 electrons, right? Because 5 minus charges brings us from a +7 to what? A +2. Make sense? Right? So now our equation looks like 5 electrons plus 8 protons plus permanganate minus 1 makes manganese 2 plus 4 waters. So notice that since this is the reduction one, right, the electrons are being added to which side? The left side, right? But on the oxidation half reaction, where were the electrons added to? The right side, okay? Now we combine them all together, the two halves all together, right? We have this guy here, right? And we have this guy here, right? And the thing that we have to do now is to make it so that we have the same number of electrons on both sides. Because on this side, we only have 2 electrons, and then on this side, we have 5 electrons, right? So what's the most common multiple for 5 and 2? 10, exactly. So you multiply everything by 10. I mean, sorry, you multiply everything up here by 5 to get that to 10 electrons. And then you multiply everything here by 2 to get that to 10 electrons, right? And so that gives us the following. Okay? So now we got 5 oxalates makes 10 carbon dioxides and 10 electrons. And then 10 electrons plus 16 protons plus 2 permanganates make 2 manganese 2s plus 8 hot waters, right? Then we add both of them to each other. We add both of those reactions to each other, which is as easy as just putting everything that's on the left side together, and everything that's on the right side together, right? So now we get this equation here, right? Where it's 10 electrons from the manganese side, right? 16 protons from the manganese side, permanganate side, two permanganates, right? And then five oxalates on the left side. And then on the right side, we have the two manganeses, plus twos, plus the 8 waters, plus the 10 carbon dioxides and 10 electrons. Notice that the 10 electrons are on both sides now, so you have balanced number of electrons on both sides, right? Or the same number of electrons on both sides. Okay. Excuse me. So after we have this entire equation, right? After we have all these equations, what we can do is, since we have not discovered, but we have figured out the number of electrons being transferred, we can actually cancel out both of those electrons, right? Because we know that those electrons are there. We can just cancel them out. So what happens is that at the end of this process, if you don't have the same number of electrons on both sides, you've done something wrong, right? That's how you know you've done something wrong, okay? So you can get rid of the electrons on the side, you can get rid of the electrons on that side, right? Just subtract them out on both sides. This is the only time that you actually subtract anything. You subtract out the electrons, right? After you get the same on both sides. And then that leaves us with our final equation, which is 16 protons plus 2 permanganates plus 5 oxalates gives us 2 manganese 2s, 8 waters, and 10 carbon dioxides, and a partridge in a pear tree, right? So at this point, you can go through and add up all the charges and add up all the different individual atoms, and it should be the same on both sides, right? So yes, redox reactions, when you balance them, are much more complicated than doing a regular chemical equation, right? But as long as you follow the steps, it should be pretty simple, okay? Right? Start out by, let's go over real quick one more time here. Oopsies. Start out by splitting them up into their half reactions, right? Remember, you split them up into their half reactions. So the manganese and the permanganate to the manganese, right, go together in the reduction reaction. The oxalate and the carbon dioxide to go together in the oxidation reaction, right? First thing you do is you just balance everything normally without balancing any of the oxygens or the proton or the hydrogens, right? You do the coefficients like a normal chemical equation, right? Then you balance out the charges with electrons, -2 over here, so you need a -2 on that side, right? Same thing with this here. This was already balanced with all the other atoms except for oxygen, so the only thing you had to do here is add in the 4 waters to make oxygens. But the problem with adding in 4 waters is you end up with 8 protons here, so you have to add 8 protons over here to balance that out, right? Now you have the same number of atoms on each side, but you still don't have the same number of charges on both sides, right? So then you've got to go and add in 5 electrons on this side to balance out all the charges. Excuse me. And then you go through and combine the half reactions, and then combine the half reactions. But the first step in combining the half reaction is to make sure you have the same number of electrons on both sides. So in this case, it's going to be 10 for the lowest common multiple, right? Multiply that by 5, multiply that by 2, and you get 10 electrons, all the numbers, right? And then you get the this equation here, right? You get that equation there when you put it all together. And then after you put it all together, all you do is you get rid of all the electrons, and then you get the completed equation. Any questions? Right? Okay, so here is your next question. What is the first step in balancing the reaction between permanganate and oxalate? Balance the oxalate to carbon dioxide oxidation half reaction. Balance the permanganate to the reduction half of the manganese reaction. Determine the oxidations of each species. Determine the species that was oxidized and reduced, or balance the charges. Beautiful. Okay, so this is the distribution right here. Kind of a mixed bag, right? But I will say right now, though, that the answer is indeed C. The answer is C, right? because before you can even balance out the carbon dioxide side, the oxalate on carbon dioxide side, and the permanganate and the manganese side, you have to figure out what species is actually getting oxidized and what species is actually getting reduced, right? Like you don't have to actually figure out what the oxidation numbers are of each of the species, but you have to be able to know which one's actually getting oxidized and which one's getting reduced, so you can actually make the correct what? Half reactions, right? Because if you don't make the correct half reactions, then you won't be able to balance each half reaction correctly, right? So um, I definitely I definitely would go through and if at the very least, figure out which species is getting oxidized and which one is getting reduced first, and then start balancing the half reactions, right? You don't have to actually figure out the oxidation numbers yet, but I would definitely figure out at least which one's which because you won't know which one's the half reaction for the redox side, the reduction side, and which one's a half reaction for the oxidation side. Okay. So, like I was saying before, right? When you're doing it in a basic solution, it's a little different. You do all the same things, right? You do all the same things as you do in an acidic solution, right? Uh, Except that once you get done balancing everything out, right? Once you're finished balancing and pretending it's an acidic solution, the next thing you've got to do though is you've got to add hydroxides to the water to the equation, right? So that you can neutralize the protons, right? So that you can neutralize the protons. Okay, you got to do that first. Okay, and so when you do that, your equation will actually make water, right? It'll turn a lot of the protons, or all of the protons, into waters, right? And when you have waters on both sides, right, you can actually cancel out the waters. Okay, you can cancel out the waters. Okay, so so this is another situation when we subtract water, but really you just get rid of the waters because if you have the same number of waters on one side, and you have like the same number of waters on the other side plus one, then you can cancel all that out and just leave that one water left over, okay? So, and the reason why we have to do this is because when you're in a basic solution, the hydroxide is there, right? And what is it going to do? It's going to go in and take up all those protons, right, and turn it into water. So you can't just leave it as protons like we did in the acidic reaction, okay? All right, so that takes us to talking about voltaic cells. Okay, voltaic cells, right? In a spontaneous reaction, right, electrons are transferred and energy is released, right? That energy can do work if the electrons flow through an external device, and this is called a voltaic cell, right? This is called a voltaic cell. This is very similar to like when people stick like electrodes into like a lemon or a potato, right? And then they can charge their phones with it, right? It's actually pretty neat. I should have done that today. Maybe that would have gotten you more interested in what was happening. So, but I didn't think about that, right? So here in this particular voltaic cell, right, we have two electrodes. We have the zinc electrode and we have a copper electrode, right? And then we have this cool little beaker here that has tubes in between, right? It's got tubes in between, and there's a porous disc in these tubes, right? And what happens is that the blue solution, you always know the blue solution is blue. Blue solution is blue, of course it is. Copper, the blue solution is copper, and the zinc sulfate solution is the clear one, right? And then a redox reaction will occur between the zinc and the copper. And when that happens, you can actually get a current. You can get a current, right? You can get a current flowing through. It's kind of neat. Okay. Anyway, so let's talk about voltaic cells in detail now with our zinc sulfate solution and our copper sulfate solution here, right? So this is what these are. Okay, just to be clear, you need to know your vocabulary words. Okay, you need to know your vocabulary words. And so in a voltaic cell, the oxidation, right, occurs at the anode, and then the reduction occurs at the cathode, right? So when electrons flow, charges aren't balanced. So a salt bridge, usually a U-shaped tube containing salt and vinegar solution, is used to keep the balances charged, right? And so here we have, oh, here's the salt bridge right here. This is a salt bridge, okay? And so here's your zinc, right? So your zinc here is the cathode, I'm sorry, the anode, right? Your zinc here is the anode. So the zinc is sitting in the zinc solution, right? The zinc is sitting in the zinc solution over here, right? And, oh, that's so funny. Um, this side we have sodium nitrate instead of, I was hoping it would be the same thing as what we said before. I wonder why they changed it. I was hoping it would be the example of this, but that's okay. So, same principles, same principles. Anyway, so here we have the zinc side, right? And you can see that electrons, right, are moving away from the zinc, right? They're moving away from the zinc, okay? And so as electrons move away from the zinc, we call this the anode side because that's the side that's getting oxidized, right? And as electrons flow from the zinc metal in the wire to the voltmeter or the multimeter, right? We make zinc 2 ions in solution, right? We make zinc 2 ions in solution, okay? So now we have down here, right, the solution of like zinc nitrate, and we're making more and more zinc 2, okay? As the zinc is getting oxidized, those electrons have to go somewhere, and those electrons are going to flow through the wire into the multimeter and give you 7.76 volts, right? So you can actually do this in lab, which we're not going to do this in lab, but you can actually do this in the lab and see like two solutions actually making a voltage, which is kind of cool. I mean, you can't really do much with 0.76 volts, but you know, it's kind of cool to see. So we bring it over here, right? And this is the cathode side because here we're getting the electrons, right? Here we're getting the electrons, and so um, uh, the so the electrons here are getting added to the protons, and you're making hydrogen gas, right? And you're making hydrogen gas on this side, right? And so it's pretty neat that you can actually do this, right? Okay. All right. So a little bit more about voltaic cells, right? In a cell, the electrons leave the anode and flow through the wire to the cathode, which I just said that, right? So here's the anode right here, right? And the electrons flow through the wire to the voltmeter right here and over into the cathode, right? So electrons flow from the anode to the cathode, which I said that in the previous slide already, right? Cations are formed at the anode compartment. So this is over here, right? Over here, the cations over here are being formed. So in the previous example, those cations were the zinc 2s, right? The zinc 2 pluses that were being made when the zinc was losing its electrons, right? The zinc electron was losing its electrons, right? And then as electrons reach the cathode, the cations in solution are attracted now uh, to the negative cathode, right? So the cations will actually pass through and go into the other side, right? And then the cations gain electrons and are deposited as metal on the cathode, right? So in I guess in the zinc one, right? The zinc uh, the zinc the zinc ions, the zinc 2 pluses are passing through here. They'll regain their electrons, right? And then deposit themselves on this cathode, right? So eventually the anode is just going to run out of metal if you let it run forever. I don't know if you can let it run forever, but that would be interesting, right? If you put a very small piece of zinc there and see how long it takes for it to completely uh, get oxidized and become, over here, that's pretty neat. So here's your next question, right? Which of the following is not true about voltaic cells? Electrons leave the anode and flow through a wire to the cathode. Sounds reasonable. Anions are formed in the anode compartment. As electrons reach the cathode, cations in the solution are attracted to the now negative cathode. And then cations gain electrons and are deposited on the metal cathode. The most of you got that one right. Good job. You paid attention to my thing, right? To my lecture. Most of you did. Anyway, most of you paid attention and got that one right. In fact, anions are not formed in the anode compartment, right? What's actually formed in the anion compartment? I mean, what's actually formed in the anode compartment? Cations, exactly. See, electrochemistry is so easy compared to everything else, right? I mean, I'm running out of excitement for it, but it's so easy, right? So there's this thing called the electromotive force, also known as EMF, right? EMF, not to be confused with the stuff that they use to detect like ghosts, What's that called? EMP. No, not EMP. EMP is electromagnetic pulse. EMV. Maybe it is called EMF. Electromagnetic frequency. Yes, so I'm pretty sure it is EMF, but that EMF is actually electromagnetic frequency. This EMF is electromagnetic, no, electromotive force. There we go, electromotive force. So what is electromotive force? What? Thank you. Anyway, so water, right? Water flows spontaneously in one direction in a waterfall. Okay. So comparably, what do electrons do? They also flow in one direction, right? Spontaneously in the redox reactions from a high to low potential energy, right? From a high to low potential energy. So in your biology classes, have you used anything that for like gel electrophoresis before? Gel electrophoresis? Yes. You add in DNA to the gel and then you watch the DNA flow. It's the same thing. That's electromotive force, right? The thing that's moving the DNA on the gel is the fact that electrons are flowing, right? But then DNA also has a very negative charge because the backbone is made of a phosphodiester backbone, which is very negative, right? So they all flow together, right, from the negative side to the positive side. And that's how DNA gels work, right? Protein gels work the exact same way. And that's what we're talking about right here. This is called the electromotive force, right? So notice, again, we have here an anode, right, which is high potential energy. The electrons flow, light a bulb, and then into the cathode, right? So from high potential energy to low potential energy, right? So if I have a true/false question for you that says that electromotive force says that the electrons will flow from a low potential energy to a high potential energy, is that true or false? I said low to high, but all right, whatever. Oh, your brain was focused on the picture, not what I was saying. Yes, but if I had a true or false question and I said it was going from low to high, that would be what? That would be false. Exactly. Right. So anyway, all that is to say this, right? Uh, the potential difference between the anode and the cathode is called the electromotive force, right? The electromotive force. It also has the thing called the cell potential, right? It's also called the cell potential, and it's designated with this little thing here called the E cell, right? The E cell, right? And it's measured in volts. 1 volt is 1 joule per coulomb, right? So when you see 1 volt on your, like for example, a double A battery has 1.5 volts, right? 1.5 volts, right? That's the same thing as saying 1.5 joules per coulomb, right? And that's the electromotive force of the battery. Make sense? Right? Good stuff. See, you're learning so much today. So much. So, which of the following is true of EMF, right? The potential difference between the anode and the cathode in a what the heck? I forgot to put something there. Maybe that's the one that's I didn't finish that answer. It is also called the cell potential. It's measured in volts, right? That was a mistake. I wasn't trying to trick you there. I don't know what happened to the end of that answer, right? The answer here, since I messed this one up, should be all true. So I don't know what happened there. So sorry about that. Yeah, it should be all true. I guess I was when I was copying and pasting, it got cut off, right? No, it's D. It's supposed to be D. It's supposed to say the potential difference between the anode and the cathode in a cell is known as the EMF. So it should be D. So since I screwed that one, I screwed the pooch on that one. We'll keep going. Keep going. So now that you know about potentials, there's this thing that we call standard reduction potentials. And the standard reduction potentials are the reductions of many electrodes that have been measured and tabulated, right? And the values are compared to the reduction of hydrogen as a standard. And these are at standard conditions. And remember, I told you about knowing what the standard conditions are a couple weeks ago, right? The standard conditions are at 1 molar, 1 atm, and 25 degrees Celsius, or the Kelvin equivalent, right, of 25 degrees Celsius, which is what? What? You just making up numbers?
273 Kelvin. Right?
Yes. Plus 25. 289. Oh, wait, 290, 298. Sorry. I got dyslexic there. 298. There we go. Or what is that called? Is it called dyslexic or is it called dyscalculic? Yeah. Yeah. It's okay, time out. It's 298. It should be 273 plus 25. Plus 25, which is 298. Where does the 0.5 come from? What? Where are you getting the 0.5 from? You must be. No, well, to change anything from Kelvin to Celsius, you just add the 273. So if you were at 25 Celsius, right, then you just add that to 273. Does, does that make sense? Where are you getting the 0.5 from? That's maybe that's true. But I only say that because a lot of times in the problems I'll give you, it will be in Kelvin. Okay? Okay, it will be in Kelvin. So, okay, I apologize for this here. For some reason, when I opened up this file, all my things got messed up. So these little AE looking things, right? They look like American Eagle logos, like the clothing company. Those all should be arrows. Arrows, arrows, arrow, arrow. All those should be arrows. Okay, all those should be arrows. I don't know why those arrows became A&E logos, right? Or it could be A&E the channel, right, where you watch Hoarders and what else was there on A&E? Storage Wars. Pawn shop? You mean Pawn Stars? I thought that was on History Channel. Is that on History Channel? I don't know. Anyway, so the point is here, know that all these standard reduction potentials are based on hydrogen being the base, right? And these numbers here, right, are the standard reduction potentials for example, fluorine getting reduced, becoming two fluorides, right? Or manganese permanganate right here, right? And becoming manganese, right? Getting reduced, right? So obviously it's a reduction potential. So all these things are getting reduced. You can see electrons being added to them and then becoming, for example, silver 1 here gets an electron added and becomes silver solid, right? And that's a reduction potential of 0.8. So you don't have to memorize these numbers, but I do want you to notice a trend in the numbers, and we'll talk about that in a second, right? Again, I don't know why I did this, but again, all those A&E logos should be arrows. My apologies there. But I just want you to see this here based on hydrogen, right? Or two hydrogens or two protons get two electrons, they become H2, right? That's 0, right? So everything else is based on 0 reduction potential, which is hydrogen, okay? And this is just a continuation of that chart, which you can look at it more later, right? So, all right. So the standard hydrogen electrode, okay, which we saw that a second ago when we were talking about the zinc thing, the zinc voltaic cell, right? So the reference here is called the standard hydrogen electrode, which is also known as She. She. That reminds me of that drug that's on TV. What is it? Something HER2 negative or something? You know what I'm talking about? Something HER2 negative, whatever. Anyway, by definition, as a standard, the reduction potential of hydrogen is 0, right? And of course, that's at 1 molar, at 1 molar and at 1 atm, right? And so here you can see the She, or the standard hydrogen electrode right here, right? And we've got platinum here, right? And some protons here, right? and then platinum is getting getting oxidized, and hydrogen is the protons are becoming H2 in this reduction, right? On the other side here, though, we have H2 molecules reducing the metal, right? And then they're getting oxidized, becoming protons, right? So the She as a cathode, protons are being reduced to hydrogen gas, but a She as an anode, right, hydrogen gas is being oxidized to a proton, okay? And so that's what all the standard reduction potentials are based on, okay? And so that brings us to this last slide I want to talk about today, and then we'll have one question, and that'd be it for today, okay? You can actually, don't leave yet, we have one question. Are you leaving or are you stretching? Oh, okay. I understand. My back hurts too. I went all out with my Christmas decorations this year, and my back is killing me. Anyway, so you can calculate standard reduction potentials, right, by doing the reduction potential for the reduced of the cathode minus the reduction potential for the anode, right, and that will give you the entire reduction potential, the standard reduction potential for the entire cell. Okay. So that's an equation you'll need later on in life, which we will talk more about in more detail on Wednesday. So the last thing for today is this question here, right? Which of the following is not true about standard reduction potentials? Okay. The values are compared to the reduction of helium as a standard. Standard conditions are 1 molar at 1 atm, 25 degrees Celsius. By definition, as the standard, the reduction potential for hydrogen is 0 volts. Or you can calculate the cell potential at standard conditions through the equation of the E cell equals the E reduced of the cathode minus the E reduced of the anode. And this is our last thing for today. Huh? Still waiting for 5 people. 4 people. I guess I'm not waiting for 8 people anymore. Now I'm waiting for 7 people. So 2 more people. 7. Oh, okay. Everybody's there. Everybody's there. Okay. The distribution here is everybody except for one person got that one right. Yes, exactly. Good job. Good job. People paying attention. The answer here is, in fact, it should be hydrogen is used as the standard, right? This is the correct equation, so it's not D. A is correct. Good job. Have a wonderful day. This ends our lecture. Good luck in discussion section.